So before we start chapter 7, do you guys have any questions on partial fractions? You guys doing okay on those problems on the homework?
So far,
Okay. Alrighty. No, let's get started then. And if you guys have some homework problems towards the end, after class, we can talk about it. All right. So 7.1. So let me show you the overview. Close that partial fraction thing. Dang it. Where is it? Okay, here it is. So let me just show you real quick before we start. You guys see the PDF?
Yes, I see it.
Okay, there it goes. All right, so we're going to talk about the basics of angles and arc length. So nothing too crazy, but this, so we get used to the notation. So we always start on this side. This is called the initial side, and I'll write this down in just a moment. Then we're going to travel some alpha or theta angle, mainly be using theta when we after this section. Wherever we start is called the terminal side. So we'll talk about that. If we go this direction, it's considered to be positive. If we start here and then go downward around, it's considered to be negative. Okay. Also, you can see that there's many ways you can get to the same side. So if I want to get to this spot right here, I can go this way, or I can go that way, or I can go around past it and then land on there again. So you're going to see, just like when we start doing the trig functions, that they're very periodic. They just keep on repeating. Okay. So let's start writing down some notes. So that's the big picture on understanding the angles. And then we'll talk about quadrants. Got my pen. Okay, 7.1. Fix the focus here. Angles, arc length, and circular motion. Okay. All right, so let's write down here, draw this real quick from the notes. So as we said earlier, this is called the initial side. Right. And I'm going to use theta because that's pretty much the angle, the Greek letter we're going to use entire semester, the most common one. So I'm going to go this way, some theta. Okay. So going that direction, we consider that to be a positive angle. It's also technically going counterclockwise. So counterclockwise will be positive. All right. Now, if this is our initial side, going this direction to my terminal side, right, this is a negative angle. Going clockwise. So if we go clockwise, that is negative. Okay. Now for the Cartesian plane, or the X and Y axis, we need to know when X and Y are negative. So X and Y. So we should all know that this is called the first quadrant, right? And in the first quadrant, both X comma Y are positive. So I'm going to use plus comma plus, so you know they're both positive there, right? X, Y. Quadrant 2, remember, going counterclockwise is positive, so this is 2. This is negative comma plus. So X is negative here. 3. Everything is negative here. Oops. Put a little back. Fourth quadrant, the X is positive and the Y is negative. Okay, those are some quick notes before we start any examples. All right, things we're going to need for the future problems. Here are some extra formulas here. So one counter clockwise, the number 1. Okay. 1 degree is equal to 60 minutes. 1 minute is equal to 60 seconds. Okay. Quick note, revolution is equal to 360 degrees. So that'll come up later. So when you see in the homework or in the examples, we have for 40 degrees, 60 minutes and 10 seconds, right? And there's some unit. We'll need to convert it using this information. Okay. So we will refer to this later here. So it'll be as degrees, minutes, seconds. It'll always be in this order. I like to put the formulas at the beginning, that way we can keep referring to them later. So that's my first one. First set of formulas. Now let's do arc length. So for a circle, of radius r, and a central angle of theta, radians, subtends an arc, whose length is S equal to R theta. So arc length is basically the distance around the circle. So if you have something like this, right? Let's say you have some radius. Actually, let's make it a little further. Let's say you go all the way out here. So this distance right here, that's S. That's my arc length. Okay, so just how far did I sweep across? That makes sense. So that's what this S is referring to. And we'll do some problems on calculating that a little bit. But let's write down all our formulas first. Okay. Also, 1 revolution is equal to 2 pi radians. 180 degrees is equal to pi radians. One degree is equal to pi over 180 degrees. 1 rad is equal to 180 degrees over pi. Okay. Let me check something really quick. Area of a sector the area A of the sector of a circle of radius r formed by a central angle of theta radians is A equal to 1/2 r squared theta. And the sector is basically this guy here. This area in here. Basically if you took a circle and took out a pie, little slice, that is the area that we're interested in. Okay. Oh, wait a minute. Let me know if you guys cool if I turn the page, or if not, I'll wait a little bit.
I'm good.
Okay. Well, let's do example 1 then. Convert the angle in degrees to radians. So let's start off pretty simple. So the question would be 45 degrees. So change that guy into radians. So whenever you do use formulas to find like arc length or area, etc., you need to be using radians because degrees is not really a true unit. Yeah, this is chapter 6, Kennedy. Okay, so all you have to do is use the formula that I gave you and multiply by that conversion factor. So if you have 45 degrees, I need to multiply by pi over 180 degrees. So make sure whatever you want to cancel. So if I want to get away from degrees, then I need to have the degrees on the bottom. So 180 is down here. Degrees. So the degrees cancel, leaving me with 45 pi over 180. That reduces, right? 45 goes into 180 4 times, leaving me with pi over 4. So this is radians. Okay. So write you a little note here. So conversion factor degrees to radians.
Sir?
Mhm.
Is it appropriate to put the lowercase r next to that after you're done?
For this guy?
Yeah,
No, that's just radians is basically unitless.
okay, so you don't need to put like a lowercase r indicating that that's radius or anything for that?
No, you don't have to.
Okay,
If you were to divide pi by 4, you could write a decimal of rads, R-A-D-S, but it's understood and that it's not really unitless, that it's unitless, so that's is just fine. So to go from degrees to radians, you have to multiply by pi. That's a weird pi. Pi over 180. Radians to degrees multiply by 180 over pi. Okay, so now let's go the other direction just for the practice. So that is a little note for these types of problems. Example 2, convert the angle to degrees. So pi over 2 changes into degrees. So multiply by 180 degrees over pi. So I want to cancel the pi and be left with degrees. So these will be gone, leaving me with 180 over 2, which is 90 degrees. So not too bad, right? So you have a few problems in your homework that just has you do conversions like this. The first few problems will be about like definitions. So just look over the definitions of in the book. But after the definitions, you'll have questions like this. Okay. So now let's do converting from degrees, minutes, and seconds to just degrees. This one's a little weird. You'll have a few of these in there. Convert the angle to a decimal. Okay. So if you see this type of problem, 36 degrees, 13 minutes, and 56 seconds, you're gonna have to convert to only degrees. So the way I want you to think about it, it's kind of like, let me see, like a ruler measurement when you have 2 feet and like 1/8, right? You've heard those measurements, right? 2 feet and 1/8 inch of an inch or something, whatever. So whenever they say that, or for example, 1 1/4, 3 1/2, all those words means the same thing, right? You add them. So it's similar to that here. So this is the same as saying, well, let's write it separately. This is the question part. 36 degrees plus 13 minutes plus 56 seconds. So what I want you to do is remember the formulas from the other page and input them here. Okay, so we said that a minute, right? Let's show our work here. 36 degrees plus, so this is the same thing as saying 13 times 1 minute, right? Plus 56 times 1 second. Does that make sense so far? Okay. So now input what was a minute. What was 1 minute? Right? 1 minute is the same as
1 degree.
yeah, 60. Yes, 1 degree. Let me double check everything. Let me double check that formula. I feel like there's something missing. One moment. I mean, this is just an extra step. I'm just doing algebra basically. So if I divide both sides by 60, then I know that 1/60 degrees is equal to 1 minute, right? I could solve for minutes. And this also implies that yeah. So let's use this idea. That'd be better. So it makes more sense when you look back. So right here, 36 degrees plus 13, that's the same thing as saying 1/, We said 60 degrees, right? You agree with that so far?
Oh, yep.
And 60s, let's see here, 60 double quote. So what was the seconds?
One minute equals 60 seconds.
So that would mean that how many seconds in a minute?
60.
So let's see if this conversion is right. So whenever you have the double quote, I want you to substitute. I guess I remember now. What we're doing is changing it into the same units. So this is a fraction of a minute, which is then in degrees. So whenever you have the double quote, use this unit here. You have a single, use this, and this will come from solving it here. Okay, I don't want to confuse you guys, but it's easier to use that formula. So if you solve for it, you can get it here. Okay. Anyway, let's
Okay.
do
I'm sorry, I hate to ask, but could you please solve that just so I don't get it wrong later, just so I can like see it done real quick?
what the minutes?
The seconds,
Oh, sorry, yeah, the seconds. Sure. Give me 1 second.
just so I can see it and not be wrong later. Otherwise, it'll take me like double the amount of time to figure it out.
No, I hear you. Let's do it. I just have to cram it in here a little bit. So we have what? 1 minute is equal to 60 seconds, right? So, but we also know that 1 minute is equal to 1 over 60 degrees. So what we're gonna do is use this conversion here. So 1 minute over 60 should have left more space, darn it. If you divide both sides by 60, we're going to have this here. Right? A 60th of a minute is 1 second, correct? Now, if you go a step further, we know that this, right? That's the same as saying times a minute. So you replace it with 1 over 3,600 degrees. Okay. Does that make sense? Or do you want me to do it on the other page?
Um,
Can you do that again?
please.
Please, because I don't get that.
I mean, you don't need to do that every time. What I want you to do is whenever you see 1 second, replace it with this. Just make sure that this will always be that. But the reason is that formula, okay? So, but just for fun, because you guys want to know. 1 minute is equal to 60 seconds, right? And we need the fact that 1 over 60 degrees is equal to 1 minute. There we go. Yeah, using this idea. Okay, so if I divide both sides by 60, I will have 1 over 60 minutes is equal to 1 second. Okay. Then I need to change this to 1/60 times a minute. So I can do the next step. Make a little, this is a side note here. So this is going to be replaced with that. So we have 1/60 times 1/60 degrees. So all of this is equal to a second, right? So that's why it's equal to 1/3600 degrees. That's why you can substitute 1 minute, 1 second for 1/3600 degrees. Because 1 minute is equal to 1/60th of a degree. So therefore, a second would be 1/60th of this, which is 3600. And if that bothers you, just remember, all you need to do is substitute this, okay? But if you want to know why, this is why.
So that 1/3600 is literally just 1 second in degree form.
Yeah, this is how you derive that fact. Does that answer your question as to why this is the
Yeah.
case? Okay. Anyone else have a question on that? Okay, so we'll get back to the problem. You guys are cool, right? So far, up to this step? Okay. All right, so this is a derivation of y 1 second is equal to 1/3600 degrees. All right, so I'm gonna have to copy paste that over here. So we had 36 degrees plus 13 times 1/60 degrees. Remember, we're trying to get everything into degrees. That's what we're doing. Plus 56 times 1/3600 degrees. So all you have to do is divide this out. So the first one will be we're going to round to, let's say, 2 decimal places because they have to tell you. Otherwise, we'll have a ton of decimal points. Let's assume 2 for this question. I didn't tell you at the beginning, but here we are. So 13 times 1/60 on your calculator, that will be 0.216667, or something like that. 1, 2, 3, 4, yeah. 56 times 1/3600, that's 0.015556 degrees. So if I round to 2 decimal places, this would be 0.22 plus 0.02, right? So it should be about 36.24-ish. Okay. It depends on the rounding, how this is going to go. But the process, this is the process, okay? Is there any question on this? And how to go from degrees, minute, seconds to just degrees?
I thought this was going to decimals.
Yeah, it's degrees in decimal form. It's technically still degrees. Let's see here. Where was that note? Oh, yeah. Here it is. Yeah, so let me show you a homework question really quick. This is number 15 and 7.1. So see how they tell you. I should have said decimal degree form, but I mean, whatever. Round to 3 decimal places. So this would be the key when you're simplifying it. Okay, so be careful. Okay, any questions on this one? You guys want to do another one?
Sure.
Okay, just in case. Convert. This time, let's try going from an angle to degrees, minutes, seconds. This is a little more difficult. Let's do that instead. Convert the angle to degrees, minutes, seconds. Okay. So what we're gonna need is these formulas here. Here's the question. 53.694 degrees. So there's degree in decimal form or decimal degree form. We're gonna need this guy right here. 1 degree is equal to 60 minutes. 1 minute is equal to 60 seconds. Okay. So 53.694 needs to be changed into 53 plus 0.694. So you separate the decimal. Okay. So this is going to be the degree part in front, the capital D. So then we got to solve for the minutes and the seconds. Okay. So let's see here. So what you want to do is multiply the decimal piece by 60 minutes. So it's time to pull out our calculators, I guess, so you can see it. So that'd be 41.64 minutes. All right, so that's what we got. So now we're going to take off this decimal and convert that piece as 41 minutes plus 0.64. So multiply that decimal times 60 seconds. It's the same deal. 0.64 times 60. So that'll be 53 degrees plus 41 minutes plus 38.4 seconds. So at this point, you just cut off that decimal because we're not going further than seconds. So the answer will be grouped together as 43 degrees, 41 minutes, 38 seconds. Okay, does the steps make sense?
How
Yes,
did you
sir.
get the 38.4?
Where did I get it from? Or what'd you say? Sorry.
Yes, where'd you get it from?
Oh, okay. So what we're doing, right? Is we're taking the decimal parts and multiplying that by 60. The first time we did 60 minutes, right? We cut off that decimal of 694. And then we got a new decimal. So we cut the 6.64, separated it, and multiplied that by 60 minutes. Sorry, 60 seconds. Keep mixing that up. So that'll be 38.4. So that came from just multiplying the minutes. And then at that point, we're done. We just get rid of the 0.4. So we're converting pieces of the decimal at a time. Okay.
Why do you get rid of the 0.4?
Because if I wanted to use it, I'd have to go to like the next order of something smaller than seconds, like milliseconds or nanoseconds or whatever. And we're only going to deal with degrees, minutes, seconds here for these types of problems.
Okay, so we wouldn't be marked incorrect for just ignoring
No,
any 0.4, basically? Okay.
no, you shouldn't be.
Would
Is it
you round if the point,
Sorry, you
if
go
it
ahead.
was like a 0.6 or 0.8, would you round it?
I think you should. But I am not sure what the homework will take. I mean, I would take it on an exam either way because it's so small. But the homework might be weird about it. I'll have to see.
So if we end up getting marked wrong on the homework for something like that, that wanted to be rounded up or down, would you help us go in and correct that?
Yeah, I can. Just let me know. That way I have I'll know from now on because this is a brand new homework that we just made. So I don't know the rules just yet. We had just switched over to a new publisher. So I'm still learning well, I'll be learning the how it works with you. At least that type of stuff, like the inputs, not how the program works. But anyway. But yeah, if something seems like unfair, of course I'll give you points. It's not a big deal. Just let me know. Okay. Any other questions on this one? Is that okay? All right, let's move on to arc length and area of a sector. And that's pretty much 7-1 for the most part. Let's see. Yeah. One moment, double checking. Yeah, okay. So find the length S of the arc of a circle of radius 75 meters, I guess, subtended by the central angle (30°). So what we're going to need is S equal to R theta. Okay. Now the R is the radius, which they gave us as 75 meters. Theta is equal to 30°, right? Okay. Remember we said though, we can't use degrees, so we're gonna have to convert it. So multiply this by pi over 180. That would give us 30 pi over 180, which would be, how many 30s go into 180?
6.
Yeah, 6. So we need to use radians for this formula. Okay. All right. And visually, just so we have the picture, we have 30° is about right here. So we're going out 75 meters. Now we want to know how far did we arc? What is S? Okay, so S will be equal to 75 meters times pi over 6. So this is the reason why we don't write the R, because it's going to be in meters, the distance, not meters times radians. This will be 75 pi over 6 meters, which is about 39.27 meters. Any question on that problem? Does that seem okay?
So far, so good.
Okay. Alrighty. So let me look at, well, yeah, let's do area next, and then we'll move on to something a little bit different. Yeah, they do ask about area. So let's do that. find the length S and area A. This time I'll give you a little picture here.
Can you move the paper up?
Oh, yes, sorry, couldn't see where I was writing. Oh, sure. Oh, before we get there. So in order to get, sorry, someone asked a question about theta. So 30 degrees must be converted into radians before we use it. So what you do is you multiply by the conversion factor. So it's very similar to example 1 over here. You remember? So 45 degrees, you always multiply by pi over 180 if the degrees is on top. So if I'm going from degrees to radians, this is what you multiply every single time. So we had 30 degrees. So multiply that by pi over 180. All right, so this is over 1 technically. So you just multiply across. Degrees cancel. 30 over 180 reduces to 1 over 6 pi 6. Once it's in this form, you can plug it into the formula. Otherwise, you can't use it. You cannot put 30 degrees in here. It's going to come out wrong. So whenever you use the arc length formula or area, and you want to go from degrees to radians, you multiply by this. So if you need it in radians, you will multiply by pi over 180. And you need it for these two formulas, S and A. But if it's already in radians, you don't have to do anything. Just plug it in like this one. It's pi over 4. This distance of my crappy circle is 2 feet. So we have to find two formulas. So S is equal to R theta for the arc length, and area is equal to 1/2 times R squared theta. So this will be 2 feet times pi over 4, since it's in radians, we're good. That will reduce to pi over 2 feet, which is about 1.57 feet. Sorry, no, gotta raise that up a bit. So now this one, just plug in the R and the theta. Theta must be in radians. So if it isn't, convert it using the factor. So R is 2 feet squared times pi over 4 radians. So 1/2 times 4 feet squared times pi over 4 will equal 4 times a fourth will cancel, leaving me with pi over 2 feet squared, which is approximately 1.57 feet squared. So all we're doing is plugging into a formula. You can use your calculator anytime you want. Just remember your units, right? Remember the units. This is distance and this is area. Any steps that you didn't see on any part? Is it okay?
Can you just give it a second? Just a second.
Is it just coincidence that they turned out to be the exact same answer?
Yeah, that is big time coincidence. That never really happens.
That sucks.
Sorry. No. In hindsight, now that you said that, I'm like, probably should pick different numbers next time. It's because I picked 2 feet. That's probably what did it. Yeah. Whatever. It's okay. Just luck. Okay. Oh, way too many questions in this homework. I'm gonna delete some. 35 questions.
Oof.
It's way too much. I'm gonna have to delete questions as we go along. I think whoever made this really piled it on. One moment, please.
It's probably made for people without jobs.
Could be. Yeah, I'm gonna trim it down each section. If you see it, remind me as well at the end of each chapter. Like, don't forget to trim the homework. I'm gonna keep doing it every time. Let's see here. There's a couple of questions about definitions. I'm gonna let you, when you click the problem or example, it'll give you the definition. So I'm gonna move on from that. Let's see here. Let me give you some formulas at the end of 7-1. Before I forget.
This is really 6-1 though, correct?
Yeah. I'm gonna have to change my notes pretty soon. They changed the chapters on me. Still 6.1. Forgive me if that's confusing. Linear speed. So suppose you make lines for a reason. Suppose that an object moves on a circle of radius r at a constant speed. If s is the distance traveled in time t on the circle, then the linear speed which we will call v of the object is the following. So v is equal to s over t. So if we're going around and around in a circle, the linear speed would be s over t. Or s is still the same s from the arc length, okay? Which makes sense if you think about it, right? Like if you think of speed in a straight line, you have distance, let's say 10 miles, and if you travel over some time period, that'd be 10 miles per 1 hour or something, right? 10 miles an hour. So same deal here. You have some speed per some time. So this could be 10 meters per second or whatever. It's just, you just need to remember that this is around and around a circle. Okay. Or picture a tire spinning, right? What's the speed of that tire? It'll be this. Some point on the tire, I should say. Okay. Definition. Angular speed. The angular speed we're going to use omega. They look like W's when I write them, but whatever. That's what the book wants to call it. The angular speed W of an object is the angle theta. Of course, theta is still in radians, not degrees. So make sure you change it if it comes up. Swept out and divided by the elapsed time. T. So basically, omega is equal to theta over t. Okay. Which is, this is in the notes as well that I sent you. So this is the speed on the arc, and this is the speed of the angle. Okay. And one example used in the book is angular speed would be something like an engine having like going to like 2000 RPMs or something. That would be your angular speed, okay, of the engine turning. Where linear speed is just you going around in a circle, how fast. Okay, does that make sense? The difference of these two?
Can you explain it one more time?
Sure. So linear speed is just the speed you go in circular motion, around and around a circle. Like if I were to be going let's say I had a circle, right? So if I went from here, so how fast am I traveling from here to here, this distance? So that speed would be along the circle, right? 2 points, that would be my velocity here, my linear speed. Okay, so this is S, and this is theta. This would be S over time, right? My linear speed. So how fast am I going along the circle will be determined by the distance over the time it took to get from here to there. Okay.
Yeah, thank you. And then for angular?
So angular is how fast, is more of a turning type of rate. So how fast the angle inside is changing as you're going around. So the angular speed would be the rate of the angle itself changing over time. So when you think of RPMs or revolutions per minute, that's a form of angular speed.
Do you mean how fast the dial goes up on your car?
Well, that measurement that you see, the revolutions on your car, the 2000 RPMs, that's the engine inside. How fast is it turning? What is the angular speed of the engine itself, the turning rate of the engine? So that dial would tell you that rate. All right, so let's look at some examples. Let's see here. We still got some time. We'll find some good ones. Mm. Six and a half inches. Sorry, can't find my notes. I'm gonna have to just make new questions. Give me one moment. Okay, let's try this. So trying to find an easy one to start with, but I do not see one. Let's do this guy. So a 6¼ inch circular saw. Make sure I'm on the camera. Yeah. Circular power saw. Rotates at 4,300 revolutions per minute, so RPMs. That's how fast it's spinning around, right? All right, so round to 2 decimal places. Okay. So part A is find the angular speed. All right. Do you guys remember how much a revolution was?
2 pi?
360 degrees.
360?
Yeah, 360 or 2 pi, but since we're doing actual real life problems, we need to use radian. So let's stick to 2 pi. But 360 is correct. So the linear speed V is going to equal some, let's see here. So let's go ahead and change 4,300 RPMs into radians. It'll be a little easier. So this will be 4,300 times revolution, right? 2 pi radians. So we said it needs to be in radians. So that's why I'm changing the RPMs to radians. And whenever you say per minute or per hour or whatever, that means it's on the bottom per 1 minute. That's what the RPMs gave me, right? Gave me revolutions per minute. That's where this came from. You see where these numbers came from. Because I have the revolutions, or the RPMs right there, but I need to convert it to angular speed. So I need to change it to radians, right? Because what we said, radians per some time. So per minute. So that would give us 4,300 times 2 pi radians per 60. No, actually, I think we can leave it per minute. Yeah, let's do that. So let's just use our calculator. What is 4,300 times 2 pi? They don't need to write that again. Let's see. 4,300 times 2 times pi, 2 pi. All right. So it's about 27,000. Zero. Oops, that's an ugly 0. One 7.2 decimal places, so 70 radians per minute. So this is part. Yeah, getting more and more dyslexic as I get tired. I'm sorry. One minute. There we go. Any questions on part A?
Sir, you said you were doing the angular speed, right?
Yes, this should be omega. Thank you. You're correct. That's why we changed the theta to radians. I kept saying S, that's my fault. So theta, right? We had an angle of RPMs, we changed it to radians per minute. So it was actually omega. Does this make more sense?
Mhm.
Okay. All right, so let me see, it's a good question. Or maybe I can, maybe there's, I think there's a part B we could use. Find linear speed. All right. So what do we need to find linear speed? All right, we need S, right? What is S?
Speed?
It's the distance, the arc length from the last example over here. Yeah, let me show you just in case you guys forgot. It was over. Where's that thing? Oh, yeah, it's right here. So S is equal to R theta, right? So it is the distance from here to here. So once we find that, we put that over time and we'll have linear speed. So how fast did I go from there to there? That depends on the time it took to get there. Yeah, so S over T. So V is equal to S over T, which means it's R theta over T, right? What is R? What is R? Did they give us R?
No, but they give us the whole thing. All you have to do is divide it in two, right?
Yeah, exactly, right? So we have the entire saw. So cut it in half and we'll have R. So this would be 6 1/4 is the same as what? 6.25. You guys agree? Cut that in half. 6.25 and a half. So that's my R. Okay. Now theta. We found theta. Oh, actually, the Homer asks you to do this in. Homer wants you to do this in feet per minute. This is just to make it more hard for no reason. Or difficult. But let's worry about that later. So 6.25 over 2. We found theta earlier, didn't we? Right? This right here.
Yeah, it's 27, whatever that.
Yeah. So it's really just going to be 4,300 And we'll show the next step. We'll plug in that 27,000 over there. Times 2 pi radians or rads for now. Over, and that's per minute, right? So 1 minute. So multiply all this nonsense together. What do we get? Let's see. So 84,430 radians per minute. Actually, I lied. It won't be radians. I mean, technically the radians is there, so I'll leave it. But once we multiply, because radians is unitless, it'll be back to inches. Okay. So it's gonna be 84430 point. Let's see, they said 2 decimal places, so 30 inches per minute. How do I change inches to feet?
Aren't there 12 inches in a foot?
Yeah, so we must multiply by a conversion factor. So that'll be 1 foot per every 12 inches, right? So basically, double check that. Okay. Sorry, I was just I was doubting reality for a moment. Okay, so multiply this out, inches cancel. Then I'll be left with feet per minute. I must divide this by 12. So I will get 22,039.58. Actually, that's not right. Maybe multiply it again. Not 2,000, 7,000, sorry. 7,035.86 feet per minute. There we go, finally. Someone had asked a question. You talking about this 84,000 or 8? Yeah, where'd this come from? It'll just multiplying all this out here. This 6.25 over 2 times 4,300 times 2 pi gives me give me this. Any questions on any of these steps? Now the word problems can be a little more difficult, but I wanted to at least do one or so. Make sure you see that it needs to be in radians and that S is technically R theta still. You guys okay?
Yeah, I'm good.
Okay, I'm gonna try to delete some of the really difficult ones for you, try to help you out. And shorten this homework in general. But that's it for 6.1. Any questions about 6.1 in general?
Not right now.
Okay.
Not right now.
Are we okay to leave, sir?
Let's see. Yeah. Let me see here. Maybe look at 7.6.2. See if it's worth starting. Yeah, we'll stop here. We'll hit on Thursday. We'll do 6.2 and 6.3. Okay. If you have any questions, you're welcome to stay for a bit. Otherwise, you're welcome to head out.
I wanted to ask you, sir.
Mhm.
Do you know if there are still people like actually doing anything with the math tutoring lab? Because it's kind of weird trying to get a hold of them.
Yeah, you can. There's links in. I don't know if I posted it in this class, but yeah, actually I did. At the homepage, there's a link to MathWorld. So you just click it and you can pick which tutor you want to see, and they have their hours posted.
Oh,
So
is
you
that
just-
how that works?
Yeah, you just jump into a Zoom room and just ask questions. So that's how we're doing it at the moment. But once we go back to school, I don't know what's going to happen. You might be able to go in, but also maybe Zoom with maybe both options, Zoom or in person. We'll see.
Okay.
Right. But right now you can do that.
Thank you, sir. Have a good night.
You too.
Bye.
Have a good night.
Does the homework have specific due dates?
Not at the moment. Try to have it done before the next class period is usually the good rule of thumb. But if not possible, then as soon as you can. Right now, they don't think they have a date. I need to go in there and set some dates, but I'm gonna try to leave all of chapter 6 open until the end, until after your exam passes, whenever that is. Haven't decided on a date, but I'll let you know soon. So day after exam 1 closes.
Thank you.
Sure.
Have a good night.
Have a good night.
Thank you. I
Do
have
you know
no
how to use
questions.
the TI Inspires?
I'm not very experienced with them, but I can try to help you.
Because, yeah, I think it can control my entire house at this point.
Yeah, Inspires is really fancy. I mean, if you know how to use it, it's awesome, but I have to like I know they want me to learn it because I need to teach statistics with it. But I haven't.
Oh, that was the thing. Do you teach calculus?
Yeah, I teach Cal 1, Cal 2, almost. I taught it in the summer and spring, and I probably will teach it in the spring again.
I learned my lesson against my classes in the summer, but
Oh yeah, that's tough. That's tough. But yeah, I think pretty sure, like I'd say 80% chance I'll be teaching Cal 1 in the spring.
have a good night. Maybe we'll learn this calculator together because it's a little scary.
Yeah, it is. If not, I mean, we can always look up a bunch of YouTube together if you want.
Well, I still have my 83, so it's not a big deal.
Oh, okay. And that I'm glad you have something to fall back on. 83 is good enough for this class, but Inspire is pretty cool. We'll see.
I don't know. We'll see about that.
Yeah. We'll
Have
see.
a good night.